Yeah, possibly a PowerPoint. Okay. All right. Good afternoon, everybody. My name is Chad Mason, and I'll be giving you part two on electron beam melting with powders. So I have here attached is a quick 2-minute video just describing the process. It's from YouTube, and let's see if we can get it. Proxy server. How do you highlight it? The video? So you can just, yeah. They are links. You forgot the 8 there, I think. Okay. So this is RCAM's process, and from our first video that we made, we kind of went over their models. I believe this is kind of an older video, but this is making, I believe, what to be a turbine blade, and just like a lot of the other processes out there, you take a CAD model, you cut it up into a bunch of pieces. These are 100 micron thick pieces. Load in your powder on the left and right, and then you just close the vacuum chamber. Then you just rake it onto the build platform, and then your electron beam makes the part that you're trying to make. So this is kind of showing you maybe a molecular, and you just keep doing it until you get a final product. I believe that's the like preheating part, because it actually makes a chunk, and then you have to remove the powder. So it's like a 2-step process. They'll kind of show it to you when they take it out. So then you remove the part, and it shows you that it's like a big rectangle, and then you put it into another machine, and you just kind of take off all the excess parts. Interesting. So some of the dominant process variables are electron beam power, beam scanning speed, powder properties, and also in some of the things I've been reading, oxygen weight percentage plays a pretty big factor, and then build orientation may or may not. We'll kind of go over that through some case studies. So research study 1 that I was looking at is, the title is Qualification of Electron Beam Melting with a titanium alloy for orthopedic applications. The scope is to investigate mechanical properties of EBM orthopedic parts using the titanium alloys, like we said. And they're just going to compare the EBM to conventional methods such as sand casting, and determine processing factors that change part quality. And so some of the research question was, does oxygen weight percentage affect mechanical properties of the part? And this kind of blurry, I don't know, kind of chart that I have up here on the left-hand side is the different samples, and then it has oxygen weight percentage. So you have 0.10, 0.12, and 0.14. So I believe it's yeah. And then HIP stands for hot isostatic pressing, and it's industry standard for casting. And so they actually treated some of the parts. So they treated sample X and Z because apparently they actually do this to sand casting parts. So they figured that you might as well do this. And then the orientation was also changed. So we have the Z-axis and then the X and Y. And then it also shows the average yield strength and elongation. And the important takeaway there was that higher oxygen content results in a higher yield and tensile strength of the component being made. And then another research question was, does orientation during processing change mechanical properties? And basically, from the last slide, if you compare them, they actually do not change mechanical properties very much. There was a slight elongation difference, and I don't have any notes on that. So another research study was called Microstructural Characterization of Modeling of Beam Speed Effects on Titanium Alloys by Electron Beam Additive Manufacturing. Very long title. The scope is to understand mechanical properties. So the experiment, understanding the phases when changing beam scanning speed. So Arcam's machine actually has 4 settings for beam speed. We'll kind of go over those. So research question was, how do phase volumes change with respect to beam scanning speed? The experiment uses 4 different scanning speeds ranging from 214 millimeters per second to 689 millimeters per second. So over there on the right is a photo of the actual part that they made, and the part dimensions I have here. So this used an Arcam S12 machine. You can find this machine at Marshall Space Flight Center. So the actual parts that they made were 60 millimeters long by 5.5 meters or millimeters wide and 25 millimeters high, using the TI6AL4V, so the titanium alloy. And SF20 is actually the slower 214 millimeters per second, and the SF65 is the faster one, and so the other ones are just ranges in between. And the photo on the left is actual, it's the microstructure looking at alpha, beta phases. So the result from the study, so there's an equation, and it's called, I have it on the next slide. It's kind of a weird name, but it's an equation that can estimate alpha and beta phases in your actual part. And so this graph actually is the difference between the observed and the theoretical calculated one. And so kind of the take home is that SF50 was only around 6.5% difference, so not really a big difference. And then the actual study that they were doing, the important takeaway with that was increasing scanning speed results in an increase of martensite and decreases the alpha phase. So how do we use this? Well, the equation is called JMA. It's a theory to predict the fraction of alpha in the microstructure, which we might be able to better understand beam scanning speeds and understand the parts that we're actually making. Are they going to be stronger or not? Another big take-home from this was every part that you make, it doesn't actually mean that it's going to meet industry standards for sand casting. So you always want to test your parts before you actually ship them out. So down there on the bottom is actually the equation where T is time, K is 1.5, and N is 0.04. And this is for the titanium alloy. And here are my references.